everyone here. Thank you so much for coming. It's a pleasure to be here under such happy circumstances. For those that aren't familiar with the seminar series, this is part of the CaJAGWR seminar series, which is a host for talks on the topics of gravitational wave research. Today, we're very fortunate to have with us our own Dr. Alan Weinstein. Alan is a professor here at Caltech. He's the head of the Data Analysis and Astrophysics LIGO group that's here. He's been working on LIGO for over 15 years now. He's going to tell us about the recent discovery, as I'm sure you all know. So without further ado, let's welcome Dr. Weinstein.
See if this works. It does. Thanks, everybody. Yeah, 15 years. I guess I've been giving colloquia and talks on LIGO for 15 years now. I show this slide at the beginning. I always feel obliged to point out that, you know, there's no discovery to point to today. Oh, wait. There is. There is. Actually, I do have a discovery to talk about. In fact, I get to say, ladies and gentlemen, we have detected gravitational waves. Okay. I've been saying that every day for the last week and a half. Actually, longer than that. Okay. Unlike Dave Wrightsey, who would launch straight into the discovery, I'm going to take a few slides to give you just the tiniest amount of background about the context, about our detectors, and then we'll just launch into what we've observed in the first month of our 3-month first observing run of the Advanced LIGO detectors. So to put things in context, I'll remind you, because many of you already know, that gravitational waves can be observed and detected in a variety of different ways, all of which have deep involvement by people at Caltech. So at very, very low frequencies, wavelengths on the size of the observable universe, you can detect gravitational waves from the early universe using, for example, the imprint that it makes on the polarization of the cosmic microwave background. I won't say anything more about that. You can also, for higher frequency, shorter wavelength waves, such as gravitational waves with frequencies on the order of nanohertz, you can detect such gravitational waves through precision pulsar timing, arrays of pulsars observed by radio telescopes on the ground. Higher frequency waves on the order of a millihertz can be observed using space detectors, such as LISA, LIGO in space, or the Laser Interferometer Gravitational Wave Observatory. Another one of those detectors that was conceived at Caltech and JPL. And you probably know that the LISA Pathfinder, which was launched several months ago, has now reached its orbit in around L1 and has released its test masses and is starting its science program even as we speak. So it's a very exciting time for space-based gravitation wave detectors. But I will focus on our ground-based detectors, the Advanced LIGO detectors and its sister projects, and the gravitational waves that are detectable from the ground are audio frequencies, 10 or 20 hertz up to a few thousand hertz, and our targets are things like binary coalescences, spinning neutron stars, black holes and neutron star binaries, black hole binaries, neutron star binaries, spinning neutron stars, supernovas, and perhaps even high-frequency gravitational waves from the Big Bang. I will not talk much about the detectors. In fact, to hear more about the detectors, you can go to the Watson lecture on March 9th, when Rana Adhikari will be talking all about it. So I encourage you to attend. That's in the evening. I'll just put up a few slides to remind you that the Advanced LIGO detectors have 2 sites, LIGO Livingston in Livingston, Louisiana, LIGO Hanford in Hanford, Washington State, separated by 3,000 kilometers, 10 milliseconds of light travel time, oriented, well, 90 degrees, but more or less co-aligned, and operating together as a single observatory. The detectors themselves are laser interferometers. A laser is impinging upon a beam splitter, gets split into 2, and in one arm, in both arms there are Fabry-Perot optical cavities, and the light goes in, and basically this is a bottle. This isn't working so well, so let's see if I can find a better one. or not. This will have to do then. So it's basically a light bottle holding on to 100 kilowatts of circulating power. When a gravitational wave goes by into the board, it'll stretch one arm and squeeze another arm, characteristic of the strain induced by gravitational waves, and let a little bit of light out the dark port, the otherwise dark port, to our photodetector. And the light that is reflected back to the laser gets actually recycled back into the detector with a power recycling mirror, and there's a signal recycling mirror at the output port to shape the frequency response of the detector and optimize it for the kinds of signals that we're looking for. I won't say much more except to point out that the net result is that the noise in the detector that prevents us from detecting gravitational waves under normal circumstances, the noise equivalent strain is shown over here for the Advanced LIGO detectors during our first observing run. And here's frequency from 20 hertz to 1,000 hertz, so again in the audio band. And here is strain sensitivity, or strain noise, preventing us from detecting anything much quieter than that, on the order of 10 to the minus 23 or 10 to the minus 22. Later on, we'll see that this corresponds to displacements on the order of 10 to the minus 19 meters or better. One more slide just showing the laser beams and resonance in the detectors and showing that the end test masses are isolated from the ground with a quadruple pendulum suspension, which is attached to an active seismic isolation system. We can push on the mirrors using electrostatic actuators, electrostatic drive. We can also push on the mirrors using photons, using a powerful laser source. Well, it's only a waterproof laser source as a calibrator. And that's how we calibrate and measure the response of our detectors. That's all I'm going to say about the detectors. Okay? A little bit about the history of LIGO, just in one slide. You know that it's been a project pursued by Caltech since the mid-1980s. It was, of course, first conceived in the 70s by Pixar and collaborators. And at about the year 2000, the initial LIGO detectors first came online, and they ran for a decade till about the end of the end of 2010. The so-called 5th science run and 6th science run were the runs in which we achieved our design sensitivity, but we detected no gravitational waves at all. After that, we realized that we realized long before that in order to reliably detect gravitational waves, we really need a far more sensitive detector than we even knew how to build in 1990. But we did know how to build it by about 2005. We proposed to the National Science Foundation an upgrade called Advanced LIGO. We proposed it back in 1995 as well. They told us to build the initial one because they thought we knew how to do that. It took us 10 years to convince them that we knew how to build an advanced detector. You have to proceed in steps with these very complex and expensive instruments, and it worked out exactly according to plan. So we were funded for building Advanced LIGO around 2005, 2007, 2006, and then we shut down the detectors. We were dark for 5 years, building new detectors inside the existing vacuum system, inside the existing sites, and Hanford and Livingston. Everything on the inside was pulled out. And then we started in mid-2015 to shake down our newly constructed Advanced LIGO detectors. And they're pretty much identical detectors, even though they're in very different environments. Took us a good 6 months or so to shake it down well enough so that they were operating stably, relatively quietly, and starting in about September, we scheduled our first observing run for September 18th. And before that, we were in what we called Engineering Run 8, in which we were shaking down the detector, and by about September 11th, it came to the point where we thought this was pretty nice and quiet. Okay? So let's just sit and observe as much as possible until our observation run starts in earnest on September 18th. And we're pretty glad we started about a week earlier than we had originally planned. But by then, the detectors were already working pretty darn well. So now we are in the Advanced LIGO phase. We just finished our first observing run. It lasted 3 months, from September to the middle of January. We're down now in order to improve our detectors even more, maybe by as much as a factor of 2. And a factor of 2 improvement in the detector sensitivity means that you can detect sources twice as far out, which means a volume 2 cubed more. That's a factor of 8. It's worth going down for 3 to 6 months and get a factor of 8 improvement in sensitivity, and then when you come back up, you've blown away your old detector. This is not a trivial thing to do. It requires a lot of people. The LIGO scientific collaboration is now I was going to say a mega collaboration, it's a killer collaboration. About 1,000 people around the world, from just about everywhere, including many people who contributed to the detector, but mostly people who are contributing to understanding the data and the astrophysical sources from the data. So one of those detector slides that can only fit in the collaboration slides that can only fit in the institutions, not the people's names. One more thing about the Advanced LIGO detector noise, and that is that it's understood at some level. It's limited at high frequencies, above about 200 or 300 hertz, by the shock noise of our laser. This is sensing noise. It will be limited at lower frequencies by the radiation pressure of the laser power on the mirrors, shaking the mirrors. That's displacement noise. And both of these put together are a coherent form of quantum noise. One is the back action of the other. Heisenberg uncertain that back action. We turn up the laser power, we can reduce the shock noise at high frequencies, but that'll increase the radiation pressure noise at low frequencies. And we're going to play with that a lot over the next years. At lower frequencies, we struggle with all kinds of noises, such as seismic noise, the noise of the suspension, the shaking of the suspension and of the mirrors themselves due to the fact that they're held at room temperature rather than very cold. So there's thermal vibrations. This is what dominates at low frequencies. Also, at low frequencies, is Newtonian gravity. This is weather and seismic motion and trucks that go by that can shake the mirrors at low frequencies. These are not gravitational waves. These are simple Newtonian, reasonably quickly varying Newtonian gravitational noise that we cannot shield against, but we can, in principle, measure by measuring the motion and vibrations of material around the detectors, and in that way cancel those signals. And so that's an active area of research. What's really dominating at low frequencies is other complicated technical noise sources that we should be able to find and fix. The detector is moving in many ways. Only one of those ways is the gravitational wave dance. Okay? The other ways, common mode, other kinds of motions, other degrees of freedom of motion, we try to keep them out of the gravitational wave channel. They leak in. This is the leaking in, this gray stuff. Okay? And that's what we've measured. And then the actual observed noise that we measure still is above all that. And this is what we can only call mystery noise. We don't really know. We have lots of ideas, but have not found a good solid model for what it is. And this is the work that we do during those months and years of commissioning these detectors and trying to make them work better. And much of the work is at low frequencies. So I just wanted to mention that. The other thing about this noise curve, and by the way, this is 10 to the minus 20 meters per root hertz, so it's a noise amplitude spectral density. Okay? So a few times 10 to the minus 20 meters of displacement noise, which is pretty good given that everything is made of atoms, which are 10 to the minus 10 meters in size. So it requires a lot of cleverness and tricks, which we've been doing for many years. Even this noise that we observe is non-stationary. It moves around. And so here, for example, is the average over a day of the noise fluctuations. And you can see it's almost always happening at low frequencies. Now, you know, if we're looking for binary black holes orbiting each other, they spend a lot more time at low frequencies than they do at high frequencies, just before merging. So it's really important to get this low frequency noise down in order to be much more sensitive to lower frequencies from binary black holes, binary neutron stars, and especially very massive ones, which only merge at low frequencies. Okay, I mentioned that we search for many different kinds of sources, and everybody's got their own favorite, and I swear I can give you good reasons why this source will be the one that we detect first. But guess what? The source we detected first are coalescing compact binary systems. That is to say, binary neutron stars, neutron star black hole, or binary black holes. These are the strongest emitters of gravitational waves because they're the simplest. Two objects orbiting each other makes the biggest mass quadrupole moment, an accelerating mass quadrupole moment, which is the source of gravitational waves. We can also look for gravitational waves from neutron stars, isolated neutron stars, not perfectly spherical ones. They have to have some asphericity, like a mountain on them. Then as they spin, they will produce gravitational waves at one frequency, a sine wave, always on. And there are many neutron stars in our galaxy that are spinning fast enough to produce gravitational waves that in the LIGO band above 20 hertz. We will be unable to detect such signals from outside of our galaxy. In fact, spinning neutron stars, if we're lucky, we can go out to about 1 kiloparsec. Right? The center of our galaxy is 8 kiloparsecs away. So really our galactic neighborhood is our range for spinning neutron stars. Whereas these objects, being very strong emitters, we can detect out to hundreds of megaparsecs, as we'll see, or a gigaparsec. Every once in a while, there's a core collapse supernova in our galaxy that would produce gravitational waves that we'd be able to detect. It's rare, maybe 2 or 3 times a century. In our galaxy, we have a very little chance of detecting gravitational waves from core collapse supernovas in galaxies, in other galaxies. Finally, the cosmic microwave background has an analog with gravitational waves, the cosmic gravitational wave background. That is one of our holy grails, and it's at all frequencies and at all times. It's always on, coming from all directions, and it may indeed be too faint for us to detect with the Advanced LIGO detectors, unless we're lucky. So let's hope we're lucky. Okay, but what I'll focus on, of course, in this talk are binary black hole orbits. As they orbit, of course, binary black holes lose energy by gravitational wave emission and angular momentum. As they lose energy, they in-spiral, they fall closer together, they move faster by Kepler's laws. As they move faster, they emit higher frequencies and larger amplitude gravitational waves, and eventually they reach a point where they come so close together that they merge into a single black hole and produce a big burst of gravitational wave radiation, and then the final black hole, which is highly excited, rings down the way of Delmine and produces another burst. And so that's called the in-spiral. This is the gravitational wave waveform. The in-spiral, the merger, and then the ring down at the very end. And that's the kind of signal we're looking for. And for low-mass systems, the merger happens at high frequencies, and for high-mass systems, the merger happens at lower frequencies. So by measuring those frequencies, in fact, by measuring the phase evolution, we can learn quite a lot about the source of the gravitational waves. Okay, how did we find these things? Well, we have search pipelines. We have software running in real time on the data coming from the LIGO detectors and searching for signals. And again, we've got months of data, and we're looking for a blip lasting maybe a fraction of a second. It's a classic needle in a haystack kind of problem, and these signals are very weak, and you have to pull them out using the fanciest signal processing techniques that you can come up with. So we have 2 different template-based searches. These searches make use of theoretical templates like this one, and look for signals like that in the data. And of course, such a template requires you to know the masses, the spins, the location, the time, all these things. We don't know any of those things. We don't know when the signal will come. We don't know what direction in the sky the signal will come from. We don't know the masses or other properties of the black holes. So we have to search over all possibilities. So we need big fat computers to loop over all these possibilities to search for gravitational waves, weak gravitational wave signals in the data. So these template-based searches are particularly sensitive because when you know the form of the signal you're looking for, it's much easier to pull it out of the noise. And we do know what the signal is, if we believe in Einstein's general theory of relativity, for compact binary coalescences, for binary neutron stars, neutron star black holes, and binary black holes. Okay, and these are low latency. They take tens of seconds, and they allow you to find the source in the sky very, very quickly. Thanks a lot, Larry. Okay. We also have, we're looking for all kinds of signals, signals from core collapse supernova, things like that. So we have other kinds of pipelines to search for other types of signals, but in particular for short duration transients, something lasting less than a second or so, for which you don't have a reliable model, or maybe you don't believe that model, or you want to test that model, you need unmodeled searches, so-called bursts. of gravitational wave power in the time frequency plane, or in the frequency band of the LIGO detectors and above the noise. These also are done with low latency, and we have two different ones of those for redundancy, okay? Because we don't want to fail because of some bug in some code, unless, of course, both codes have a hole. All of these make use of two detector coincidence in both time and in signal morphology. And all of these searches detected the signal that I'll be telling you about, GW150914, with high significance above detector noise. Just a little bit more about the template-based searches. What we do is divide the search space into mass. Mass to binary, so here's the mass of the higher mass black hole or neutron star, and the mass of the lower mass one. This corner over here, this is a logarithmic scale, by the way, from 1 solar mass to 100 solar masses, similarly over here. Okay? Over here are binary neutron stars. We figure neutron stars are probably not going to be more than about 3 solar masses. Hard to hold up nuclear matter with 3 solar masses. So these lower mass systems are binary neutron stars. In this regime, we have neutron stars orbiting black holes, or vice versa. And in this regime, it's binary black holes. And I mislabeled that. Sorry, this is binary black holes up here. And each dot is a template. And we have 250,000 templates. In this corner, the templates are very long. And they have that phase evolution that varies from mass to mass very sensitively. So we have lots of templates in this region, closely spaced, such that if the signal falls in between two nearby templates, we lose no more than a few percent of the signal-to-noise ratio. Okay. But the signal that I'll be talking about is way over in this corner, and it is a high-mass binary black hole system, higher than we even dared to expect. Although we did have templates nearby. Didn't lie exactly on one of the templates, but in these high mass systems, the templates are short, have only a handful of cycles, 10 maybe, and so it's you can a signal that falls in between these two templates will still be captured by a nearby template with high fidelity. In fact, the higher mass systems are louder because mass is the source of gravity and therefore the source of gravitational waves, and so you get louder gravitational waves from higher mass systems. And so, if you look again here in the mass plane, so this is now linear scale, these contours show the distance at which we can reliably detect gravitational waves above the detector noise. And we can see that for this high mass system, which we'll talk about shortly, GW150914, our sensitivity is such that we could detect out to about 900 megaparsec, so almost a gigaparsec. Okay? So that's redshift of 0.2, something like that. Okay? And it turns out that the signal was loud, which means it was only about half that distance, as we will see. Okay, when you do a search like this, if you always have noise, and you have to look for a signal above the noise, these plots are kind of a little bit complicated, but here goes. Here's a sort of loudness, a detection statistic. Maybe it's just a signal-to-noise ratio in some pipelines. In the case of the generic burst search, there's some detection statistic. The larger it is, the louder it is, the more it can be separated from the noise. This is the number of events observed, and it's a logarithmic scale. Hundreds of events here for low values of this detection statistic. This is the accidental coincidence of instrumental noise fluctuations in two detectors separated by 3,000 kilometers happen to be producing glitchy noise at the same time. This is what prevents us from detecting gravitational waves most of the time. They're loud. Okay, does that make sense? There's two curves here. One of them is looking for the kind of generic transients that aren't so generic, that look sort of qualitatively like they chirp up in frequency. Okay? Whereas this green curve is more generic transients of any kind. Okay? So you can see the noise. This is all noise. And then you see an event, which sticks out here with a detection statistic on the order of 20. And it is higher than, at least for the black curves, higher than our prediction for the kinds of noise transients we would see, accidental coincidence transients we would see, in hundreds of thousands of years of observation time. Okay? This is louder than that by a lot. Okay? It has a false alarm probability on the order of 10 to the minus 7, which corresponds, if you do it with Gaussian sigmas, to greater than 4.6 sigma. Okay? Oh, sorry, this is a false alarm probability of 10 to the minus 5, which is 4.6 sigma. That's the unmodeled search. For the model search, here's the noise. Well, something here, okay? But then there's this. And this guy over here has a signal-to-noise ratio of 23, almost 24, louder than all the background, and the prediction for the background over hundreds of thousands of years of observation. Even if we let the triggers, the signals from each detector, match up with a noise transient in the other detector, that's letting this. There's a big dog, okay? It's a coincidence of two loud signals in the two detectors at the same time. A little dog would be one loud signal from this guy in one detector and another bit of noise in the other detector. Okay, those are what we call little dogs. Here's the little dogs. They're all coming from this guy, by the way. Okay? And this guy is louder than all of them by a lot. So much that we estimate that the false alarm probability is better than 10 to the minus 7, which corresponds to, in Gaussian signal language, a detection of greater than 5.1 sigma, which is the gold standard for discovering something really new for the first time. Okay? We think we've done it. Now, as we, the first question you might ask when you look at something like this, my gosh, this is so loud. Did you really expect to detect anything this loud on the very first detection? Well, let's see. Our threshold for detection is somewhere around here. And this corresponds to about 9.5, signal-to-noise ratio of 9.5. And it was observed with a signal-to-noise ratio of 23.7. So you can calculate what's the probability that the first event you see above 9.5 is greater than 23.7 in signal-to-noise ratio. And that probability is 6%. We were lucky. Not insanely lucky. This isn't a tiny probability. It's a reasonable probability. We were lucky, but not insanely lucky. Okay? And the second question you might ask is, oh, you see this loud event, surely you see some less loud event somewhere? Oh, wow. Maybe we do. This one over here, which we'll talk more about, is just above what you might call our detection threshold. It has a false alarm probability of about 2%. All right? You're not going to take that to Stockholm. But you might have an event there. And in fact, if you didn't know about this guy, you would say, well, the probability that its background is 2%, but that doesn't mean the probability that the signal is 98%. I mean, after all, the prior probability that there even is signal is 0. Then I don't care what that false alarm probability is, it's false. But once we know that events like this really do exist, then we have a prior on the rate for signal. And when we put that prior in, then we can calculate the probability that this guy is signal, 98%. So we got something, a second event. This was seen in both of the template-based pipelines. One is called PyCDC and was able to bound the sensitivity, the false alarm probability less than 2 times 10 to the minus 7, which means a significance of 5.1 sigma. The other pipeline is actually able to extrapolate all the way down underneath this signal, but through more aggressive estimation of the background, and gets a false alarm probability of 10 to the minus 11. That's a significance of 7.1 sigma. That you can take to the bank. Okay? And that's work done by many people here at Caltech, including Sergey Sachsev, Ken Blackburn, myself, and visitors here, Duncan Nietzsche and Cody Messick, and lots of other people. Okay, here's what the signal looks like. You've seen it before. You probably have a T-shirt with it. I don't, but you know, they gave away all the swag while I was being interviewed by the press or something. Oh well, say la vie. Here's the signal in Hanford. The signal in Livingston is in blue, and then we take the signal in Hanford. We have to flip it because the two detectors are oriented 90 degrees apart. So we flip it in sign, and we shift it by 7 milliseconds. And look, they lie on top of each other. Now, you wouldn't be able to see signals like this in the data if they had signal-to-noise ratio of 5 or 6 or 10. This is 23.7. you can see the signal in the data with your eyeballs, with a bit of fancy signal processing. But you can see it. It's amazing. We can also take one of our templates, our best fit template, and superimpose it upon well, actually, we can do two things. We can take these signals and reconstruct what they are in a model-independent way. That's the next slide. Okay, and that is this light gray over here. And you can see it also here, light gray. And on top of that is our template, which is in dark gray, and a simulation from numerical relativity, from the numerical relativity group here at Caltech, on top of that. And wow, they agree nicely. And furthermore, if you take the signal template, or the numerical relativity waveform, and subtract one from the other, you get random noise. And that random noise is to a very good approximation. Gaussian. And what you're seeing from these numerical relativity templates, these are whitened in bandpass. This is the template itself. This is the numerical relativity and the reconstructed template. You're seeing the in-spiral phase. You're seeing the merger phase. That's literally just a cycle or two. And then you're seeing the ring down at the end. And by the end there, these two black holes are orbiting each other at half the speed of light. And by the time they merge, you can't talk about speeds anymore. There's only one object, not two. Okay? And they're separated by about two Schwarzschild radii, about it's 50 kilometers. Pretty darn good. Okay. You can hear it. It's in the audio band, after all. It sweeps from low frequency to high frequency, like a whoop. Now, I should say that it's not right. Okay. The signal itself is lasts only a tenth of a second. It's in the detector noise. It's low frequency, and it's highly damped. Honestly, it sounds like a faint thud. Okay. Hopefully, you'll be able to hear it. But what we can do is we can take the signal and just up it in frequency. Just increase the frequency to the point where it's in the nice band that the ear responds to, and then you should be able to hear the chirp. So let's see if we can make this work. Uh-oh. You can't hear anything, can you? Okay, you can't hear anything, maybe because my sound is off. Maybe because my sound isn't set up right. So you'll have to give me a second. Oh my gosh. Okay, so darn. Just give me a chance. Output, good. I think now it'll work. Now I got to get back here. I got to pray that we get back here, and let's see if we can get it to work. Okay, the first thing here, it's hard. I can barely hear it. There's a thud in that low frequency stuff. And then, did anybody hear the thud? The guys in the front heard the thud. But then the second time around, you hear a chirp. The chirp you hopefully could all hear? Okay, enough of this. Okay, enough! Okay. The signal is sufficiently loud that you can actually fit it in an unmodeled way. You can fit it to just sine Gaussians, just wavelets, just a family of sine Gaussian wavelets. And you can reconstruct the signal pretty well that way. That's what it looks like here. And it's a beautiful fit to the template and to the numerical relativity prediction. And this is work by our very own Jonah Cannon. In the frequency domain, the signal again sweeps from low frequency to high frequency. It increases in amplitude, but it spends less and less time in high frequencies. It's speeding up. And so the actual amplitude spectral density falls as a function of frequency, the in-spiral. Then there's a merger. And then this thing over here is a damped Lorentzian. It's a ring damper. And that's at about 300 hertz, 250, 300 hertz. The frequency of an open B string on a guitar, highly damped. This, by the way, this plot is made, cut off here, it's made with data from the LIGO Open Science Center. And the LIGO Open Science Center, which you can go to, lot.ligo.org, has all kinds of information about the event and about all the papers that we wrote on it, as you'll see. And it also has a tutorial on signal processing with the gravitational wave strain data, which is, here's a piece of it. It's an IPython notebook. It's a lot of fun to play with these things. So I encourage you to check it out. You can do a lot of things and learn a lot with this tutorial. So check it out. This is the work of the LOST team, Joe McCanner, Roy Williams, and myself. Okay. You might argue, well, if you found this really loud event, surely you could have seen it in the initial LIGO detectors. Well, no. Okay, so here's a little bit of the evolution of the initial LIGO detectors to Advanced LIGO. So here's, in green, our detectors at around 2010, before our Advanced LIGO upgrade, okay, or rebuild, complete rebuild, actually. Shown in green here. There was no sensitivity below about 40 or 50 hertz, and the strain sensitivity bottomed out at about 1.5 or 2 times 10 to the minus 23. The Advanced LIGO detectors that came online in September are a factor of 2.5 or 3 times better sensitivity at high frequencies, and much, much better, well, infinitely better, at low frequencies. And now our detection band extends down to 30 or even 20 hertz, and we're going to work towards getting it down to about 10 hertz. Okay? And our goal over the next bunch of years is to get to our design sensitivity, which is another factor of 2 or 3 better than what we've achieved so far, and we're optimistic that we'll be able to do that in a variety of different ways. You'll hear more about that from Ron on March 9th. Okay, so you could ask, well, where would this event be, its signal-to-noise ratio, where would it be, not with the Advanced LIGO detectors, which have a sensitivity, this is redshift, and this is these curves here show, as a function of redshift, how loud a signal would be, a detectable signal would be. So at a redshift of 0.1, we are way below this curve, which means that we're very sensitive. The signal is very loud. But we're above this green curve. That is to say, this signal would be too weak in the initial LIGO detectors. This is the signal to noise that our friendly event would register in the initial LIGO detectors. Signal to noise ratio of about 6. Can't detect with a signal to noise ratio of 6. We need at least 7 or 8. Okay? So we would not, 7. So with the detector from our last science run, our 6th science run, with that noise level, this event would have had a signal-to-noise ratio of 7, insufficiently above the noise for detection. But in Advanced LIGO, the signal is very low. Our insensitive detector is wonderful, and we're going to make them even more sensitive. Okay, 1 event or maybe 2. Okay, so here we plot as a function of the signal-to-noise ratio the rate. You can't read this. The rate of events. This is 1. Okay, no, sorry. This is 1 event per cubic megaparsec per year. No, it isn't. It's 1 event. But, actually, it's 1 event normalized in a certain in terms of the problem. So what we see here is a function of signal-to-noise ratio, and this is a log scale. This is these are the numbers of events observed with low signal-to-noise ratio. These are all detector noise, accidental coincidence of detector noise in the 2 detectors. And then 1 event with large error bars, because there's only 1 event, in signal-to-noise ratio and in rate. 1 event with very high signal-to-noise ratio, that's CW150914, and a second event that we aren't yet calling a gravitational wave event, we're calling it a candidate event, a LIGO Virgo candidate event. It was observed in 2015 on October 12th. That event has a signal-to-noise ratio of about 13 or so. It is sufficiently above the background. That is a very good candidate. As I argued, it's something on the order of a false alarm probability of 2%, and a signal probability on the order of 98%. These 2 events allow us to measure the rate for binary black hole systems like this in our local universe. About 100, with large errors, of course, 2 events, per cubic gigaparsec per year. Okay? That's the rate that we measure. That's the bit of science that we can pull out. Okay, just in terms of rates. This rate is in fairly good agreement. It's in the same ballpark as models, population synthesis models, the core collapse supernova rate, and other ways of crudely estimating how many binary black hole mergers we might observe per year. It is not in tension with the upper limits on the rate that we set with the initial LIGO and advanced LIGO detectors. There we set a binary black hole rate upper limit on the order of 400 per cubic gigaparsec per year. And this is significantly less than that. So it's not in tension with previous observations. But really, are we sure that it's not a rare instrumental noise fluctuation? Okay, this is not an easy question to answer. You have to agonize, you have to stare at the data, you have to try to go through various scenarios of things going wrong over and over again. This took 3 months. Okay? 3 months of work. On the other hand, within just hours, we knew that the detectors were behaving quite well. Even though it was engineering like 4 days before the official start of 01. Oh boy, these are not coming out looking so good. All right, well, I'll tell you what you're looking at here. This is time in weeks since September 12th. So this is 1 week, 2 weeks, 3 weeks, 4 weeks, 5 weeks. So this is the first month or so, a little bit more than a month, of our first observational run. And this is the sensitivity of our detectors to binary black holes, something on the order of between 1,500 and 2,000 megaparsecs, between 1.5 and 2 gigaparsecs that we could detect gravitational waves from binary black holes like this out to. Here is our first event, our loud one. Here's our second one, a little bit less loud, on October 12th. And here's the stability of our sensitivity over time. And the Hanford detector in red and the Livingston detector in blue. Nicely stable. There's fluctuations. We're used to those. Nothing untoward happening. Furthermore, we observe the noise triggers in our detector. And we measure their rate. This is not looking well. Okay, here's the trigger rate in hertz. Again, over 5 weeks of observation. This is 1/10 of a hertz, 1 hertz. This is for soft noise triggers at Hanford and at Livingston. And these are louder, 6 signal-to-noise ratio greater than 8. And it's quite rare, on the order of 10 to the minus 3, 10 to the minus 2 hertz trigger rate. And not changing much over time. Okay, an occasional fluctuation. But pretty much stable sensitivity and stable noise trigger rate. The physical environment monitors, we have tons of them all around the detectors. Seismometers, magnetometers, microphones, RF monitors, power line monitors, worldwide weather, cosmic ray detectors, etc. They were all pretty quiet during both of these events. Okay, no anomalous behavior. Okay, so there was nothing obvious. Oh, and many people at Caltech worked on this, worked on really checking the quality of the data. Detector characterization, we call it. It's not a very glamorous task. It's an awesomely important task. You cannot be confident of discovering some new phenomenon of nature if you've got glitches in your detector and you don't understand them. This is a lot of work. This slide is even more complicated, so I'm going to skip it. Okay. All right, let's believe that we've got real events here, in particular that loud one is real. Okay, we totally convinced ourselves of that. There's a lot we can learn from this event. We can check for consistency between the observed waveform and the prediction from general relativity, in particular from numerical relativity. We can confirm that these signals really can't come from anything that we can think of other than extremely compact orbiting objects of stellar mass. Neutron stars, black holes, or something even weirder than that. What this tells us, especially from the very good agreement between the signal and the theory, is that black holes, that is to say strongly curved space-time with event horizons, exist. Woo-hoo, we didn't know that before. We knew that there were regions of extreme gravity. Material would fall in. As it falls in, it would accelerate, emit X-rays. We would detect X-rays with X-ray telescopes in space. Done that all the time. There's about a couple of dozen known black holes in X-ray binaries in our galaxy. Okay, as well as supermassive black holes in the core of most, if not all, galaxies. We know that. But are they really black holes? How do you tell? You have to ping them. And then when you ping them, well, they're just curved space. So if you ping them, the only thing that comes out is ripples of space-time curvature, waves, gravitational waves. Okay? We detected these gravitational waves, the stretching and squeezing of space-time. They stretched and squeezed the space that our detectors occupy. We know that what we're seeing are Einstein's black holes for the first time. Black holes exist. Not only that, but binary black holes exist. Which means we can learn a lot about how binaries form, how massive stars evolve, and how they evolve in binaries, and how two massive stars can survive two core collapse supernovas, leaving behind compact objects without blowing the other guy away. Okay? So we can learn a lot about formation scenarios. When the two black holes merge into one, that one black hole is highly perturbed. Yeah, black holes have no hair unless they just been formed from the smashing together of two other black holes. Then they got lots of hair. And they emit that hair in the form of gravitational waves in a ring band. We see it, and that tells us that black hole perturbation theory is right. General relativity is tested for the first time in the strong, highly nonlinear, and highly dynamical regime. We can also measure boring things like masses, spins, sky locations, rates, formation mechanisms, things like that. This guy is a movie. How many of you have already seen this movie? Everybody's seen the movie. I'm not going to bother to play it. What I will point out is that this movie is made by our friends here in Cahill, the SXS collaboration. Go to blackholes.org. This is a numerical solution to Einstein's field equation in a vacuum. Okay, not the stars in the background.
Play it. Cool.
Sorry? All right. It's gorgeous. It's gorgeous. It's not just gorgeous, okay? I got to say that observing gravitational waves for the first time, okay, it's a triumph for experimental physics. It's a triumph for observational astrophysics. It is a triumph for analytical and numerical relativity, and for you guys in the back row. You did a fantastic job, and without it, we wouldn't have been able to find these things and know what we were seeing, to understand it. It's an amazing confluence of experimental theory that you don't find, well, you find throughout science. That's how science advances. That's how hard science gets done hard. It's fantastic. Okay, I don't know what happened there. But it allows us, well, I'll talk more about the tests that we can do with that in a minute. Okay, first the masses. So in the in-spiral phase, we can observe the phase evolution of the in-spiral over time. And that directly allows us to measure what's called the Chert mass, this particular combination of the masses. The sum of the two masses times this dimensionless mass ratio shown here, which is 0.25 for equal mass objects. We can measure the Chert mass. That's one combination of the two masses. From the merger, from the frequency of the merger, we can infer the total mass. The higher the mass, the lower the frequency at merger. So when you have a system in which the in-spiral and the merger are both in the detection band and both measure pretty well, then you can disentangle both masses pretty well. We're in a sweet spot with this event. We can measure both masses pretty well, and what we see is, well, by pretty well I mean plus or minus 5 solar masses. What we see is the lighter one is about 29 solar masses, and the heavier one is about 36 solar masses. Okay, 29 plus 36, 65. Remember that? Remember that. 65 solar masses total. You know, with errors. The errors have some model dependence, so we take our numerical relativity waveforms and we build phenomenological models based on them. We have 2 of them. We're not sure whether they're right, but it doesn't matter. They give pretty much the same answer for the masses. Their distance. The distance to this source, well, it's hard to measure the distance to the source, although it's possible. That's a wonderful thing. And that's because compact binary mergers are standard sirens. Not standard candles. Standard candles give you a luminosity, and luminosity energy pulls off like 1 over R squared. A standard siren gives you an amplitude, and the amplitude pulls off like 1 over R. Not great. But It depends on the orientation of the binary with respect to the line of sight. Okay? So if it's face on, you get a louder signal, and if it's edge on, you get a weaker signal. You have to know. How do you know? Well, if it's edge on, you're seeing linear polarization, and if it's face on, you're seeing circular polarization, a combination of plus and cross polarization of the gravitational waves. Okay? We can measure this by disentangling the two polarizations, figure out the orientation with respect to the line of sight. It would help if we had two detectors oriented in sort of arbitrary ways with different sensitivity to the polarizations. Turns out both of our detectors are oriented pretty much the same way, but not exactly because of the curvature of the Earth. Right? So they're not exactly oriented the same. Okay? And as a result, they are a little bit sensitive to two different polarizations. They can do this disentangling, figure out probabilistically whether we're face on, so this angle is 0 degrees or 180 degrees, or edge on, 9 degrees. Well, it's close to face on. Close to face on. Another reason why it's loud. Okay? So because of that, we can infer the luminosity distance to the source, which is about 400 megaparsecs, a redshift of 0.1. Not only is the waveform is redshifted by 10%, which means that the masses are all measured 10% off. Well, we can correct that. Okay, so these numbers are actually source masses, not observed masses. The observed masses are redshifted, but because the waveform is redshifted. But we can infer the source masses up to this sort of uncertainty, this level of uncertainty. We can look and compare the in-spiral and the merger and ring down. From the in-spiral phase, we can infer what the final mass of the black hole and the final spin of the black hole will be. From the merger and ring down, the post-in-spiral, we can do the same. They agree. And we get a very good measurement of the final mass and final spin of the black hole. We get about 62 solar masses. 62 solar masses. What was that number I asked you to remember? 65. We started with 65. What happened? Okay, well, 3 solar masses worth of energy got converted by E equals mc squared to gravitational waves. About 5% of the total mass of the system was converted to energy, to gravity. This is one of the most efficient conversions of mass to energy that we know of. Corresponds to about 5 times 10 to the 54 ergs. Don't you just love astronomy? Big numbers. Okay, for the quantum gravity aficionados in the audience, 10 to the 80 gravitons. It's a lot, okay, which means we really don't see much in the way of the quantum nature. This is a pretty darn classical system. The peak luminosity, 10 to the 54 ergs per second for about a tenth of a second, outshined all of the electromagnetic energy of all the stars, of all the galaxies, of the entire observable universe, by a factor of about 50. Okay? That's pretty energetic, don't you think? Okay? These are some of the most energetic phenomena that we know of in the universe. And we've never noticed them until now. We can also locate the source of the sky. Portal. These are not telescopes. We don't point. Can't point things that are 4 kilometers long. They are antennas. They're not dipole antennas. They're quadrupole antennas, 90 degrees. And they have an antenna pattern that we know. And there's timing difference, because these things, the gravitational waves are traveling at the speed of light. They hit Livingston's 7 milliseconds before Hanford. So from timing, we can locate the source of the sky. And from the amplitude at the 2 detectors, we can do better than just a circle on the side, and we can get an arc like this. It's a lousy one. This arc corresponds to the 50% probability contour is at 140 square degrees. Okay? You're not going to be able to find that source with the Hubble telescope, which has a very small fraction of a square degree footprint on the sky. But you will be able to do it with the Zwicky transient factory, which has a 47 square degrees of field of view, just a few pointings, and you might be able to find a signal like this. At least you would if there wasn't a binary black hole. See, black holes are black, so they don't really make much in the way of light. So you're not going to necessarily detect anything with binary black holes. But with binary neutron stars, they make a lot of light. They're probably the origin of short gamma ray bursts, which we see, many times a year with space telescopes from across the universe. Well, even though this is a binary black hole and therefore is electromagnetically dimmed, we alerted partner astronomers and 20 different instruments in which this region is found. By the way, we didn't tell them I asked this. Already on the archive are numerous papers from some of our partners, including SWIFT, Fermi-GBM, Fermilab, Pan-STARRS, Pesto, Integral. Why is this cutting off PTF? Oh, yeah. Okay, well, PTF is at the bottom there. Okay, I swear it. And DECCAM, by the way. Boy. The sky localization is done, well, it was originally done by a Caltech postdoc who's moved on. Roy Williams makes these gorgeous pictures. Mansfield Castlewell gearing up ZTF for looking for the light from these signatures. And, the game here is that when you have a coalescence, gravitational waves are detected by these ground-based detectors, and about a minute or two later, we know that a gravitational wave signal is there, and we send out signals with PO event and GCNs and all kinds of signals to all of our partner optical telescopes, which can look for prompt optical emission and optical afterglows tens, hundreds of seconds, days after the event, as well as the prompt radio emission and late time our radio emission, which can last for hours, days, weeks, months, only if it's really got material, like a binary neutron star would certainly produce something perhaps like a kilonova. So this is something that we're gearing up to do, but we probably, well, who knows whether we saw something. Still waiting for those papers. With this loud binary black hole event. We need to locate the source in the sky better, and so we're building more detectors. Well, our colleagues in Italy, in collaboration with the French, are building Advanced LIGO. We're hoping that will come online in the next year. The geodetector is operating already all the time in Germany, in Hanover, Germany. It's a collaboration between the British and the Germans. And it's wasn't quite sensitive enough to detect this event, which was relatively low frequency. This is more of a high frequency detector. Our colleagues in Japan are building the CaJAGWR detector, 3 kilometer long, deep underground, underneath the Kami of the mine, near to where Super K is. And we want to take a third LIGO detector and build it in India. We asked the Australians. They said, yeah. They asked the government. The government said, we are dysfunctional. Nothing happened in Australia, unfortunately. We asked our Indian colleagues, they asked their government. Their government said, we can do anything. Okay. So that was 2011. Here it is, 2016. 5 years later, we've been waiting. The day after the event, Narendra Modi, the Prime Minister of India, sent these tweets. Did you know he tweets? Historic detection of gravitational waves opened up a new frontier for our understanding of the universe. Immensely proud that Indian scientists played an important role in this challenging quest. Hope to move forward to make even bigger contribution with an advanced gravitational wave detector in this country. 5 years, Narendra, we've been waiting for this. 5 years. Okay? Now, at the time, this was February 11th, okay, the day of the announcement. I was standing there with, talking about this with one of my ex-grad students in India, and he said, Alan, this is Narendra Modi. Don't believe anything. Ever. Okay? What is this? 17th of February, Cabinet grants in principle approval to the LIGO India mega science proposal. 5 years we've been waiting for this. It's going to happen. Yay. Okay, we can also study We can also study more about the binary black holes. They spin, and the information about their spin, which can be maximal, like very close to, what is the word? Careness. These black holes have careness. Okay, is that your word, Marsha? It's a great word. Okay. Anyway, okay. Yes, these black holes have careness, like a lot of careness. Okay, and so we can measure their spins, but we don't do it very well from their phase evolution. So this is a complicated plot over here. Shows the Kerr spin, that is a dimensionless spin, is a quantity that would be maximal that's equal to 1. Okay, here's 1, here's 0. Okay. And, it deviates from 1, but I have to tell you that this green curve over here is the prior based on just arbitrary spin directions. So it's not much different from the prior. Which means we haven't learned much from this one event. This is the component of the spin along the orbital angular momentum, perpendicular to the direction, to the orbital plane. Okay? There's also a component of spin potentially in the plane, and that spin component, along with the orbital angular momentum, would precess around the total angular momentum, which is conserved, more or less conserved. Gravitational waves carry off an angular momentum, so it's not perfect. Anyway, this guy precesses around, which means the orbital plane precesses. And as the orbital plane precesses, our detectors see more circular polarization, more linear polarization, more plus polarization, more cross polarization. It changes over time, and our detectors have an antenna pattern, and so we get amplitude modulation due to precession. We can't detect much of that in this event, because this is a very high mass black hole. It lasts in the LIGO band for 10 seconds, 10 cycles. You can't see much in the way of the precession amplitude modulation. And as a result, we really can't measure the component of the spin in the plane very well. And this just shows a fuzz of possibilities. Really, we're not measuring much. But with lower mass systems that spend more time in band, we should be able to measure the spins pretty well. And Patricia Schmidt, Rory Smith, and the SSS collaboration are the ones helping us trying to understand how to extract spin from these signals. Oh, too much. Okay, not too much. I'll just say, here's our big, loud event that we call GW150914 with a false alarm probability, a false alarm rate of 1 in, something like 10 to the 6 years, or half of that. The mass is about 28 and 36, 36 and 29, not really very significant spin. Our second event, again, has a false alarm probability of 2%. It's only 2 sigma. Okay? It's not a discovery of gravitational waves, but it is consistent with being gravitational waves. The masses are lighter. It spends more time in band. We will have a better chance of being able to measure the spins in events like this. It's twice as far away, over a gigaparsec away. Okay, I'm probably way past time, but in this complicated plot, I'd like to go over it a little bit. Okay. These are the tests of the consistency of our observation with predictions from general relativity. The in-spiral phase, here's the strength of the signal as a function of frequency. The in-spiral phase, sort of in between, and then the merger and ring-down phase. As you go to higher and higher frequencies, the black holes are getting closer and closer together. They're moving faster and faster, getting more and more relativistic. You describe this with a post-Newtonian expansion in powers of v over c, the velocity divided by the speed of light. And you can't even read this. I should have checked this out on the screen before coming here, but what you would be able to see is that each post-Newtonian order is more important at higher and higher frequencies. And then you get into a regime where post-Newtonian orbit of two point-like objects totally fails. Now you've got an intermediate and a merger and ring down. Only general relativity can break this. Now you're in a new regime of strong field, highly dynamical gravity that you can't describe as v over c. Now you're beyond the post-Newtonian. So instead you parameterize the Einsteinian prediction with some parameters. And then from this one event, we can constrain these parameters. The very lowest order post-Newtonian parameter called phi 0. You can't see it here. Here's the constraint from LIGO. This is the constraint from the Hulse-Taylor binary, which has been observing its binary very slowly orbiting each other with 8-hour periods for 35 years. Measures it very well. The Hulse-Taylor binary can't tell us anything about higher post-Newtonian orders. We're constraining those for the first time. And as we do, we constrain higher and higher orders, which means higher and higher velocities, which means closer and closer to the merger. And then finally, we get into the regime. The new regime, where this isn't about velocity anymore at all. This is about just parameterizing deviations from Einstein's predictions. And agreement is good. It's new territory. That doesn't mean that we've nailed it. That doesn't mean we've ruled out alternative theories. It just means consistency with the predictions from general relativity. Later on, we'll start working on ruling out other theories. The other thing we can do is ask ourselves, if gravitons have mass, then they will experience dispersion. That is to say, the graviton, or gravitational wave, will travel slower than the speed of light. And the higher the frequency, or the lower the frequency, the slower it will travel. Is that right? The lower the frequency, the more the mass matters, the slower it will travel. So what happens is that the waveform, because of, in the presence of dispersion, due to massive graviton, will distort. It'll compress. It'll change its shape and be different from the prediction. So we can compare the data with the prediction with this tunable parameter, the mass of the graviton. And we can limit the mass of the graviton to be less than 10 to the minus 22 electron volts, or its Compton wavelength to be greater than 10 to the 13 kilometers. That's the best limit, the best direct limit for the mass of the graviton that has ever been seen. Okay, how far? I'm way beyond time. So I'm not going to talk about formation mechanisms, except to mention that there's two that we can think of. One is the common envelope evolution of isolated binaries. Two massive stars surviving successive core collapse supernovas in a stellar nursery. But another option is dynamical capture of isolated black holes in n-body exchange interactions, like sort of, two guys orbiting each other, they might emit a lot of gravitational waves and capture each other, or they may kick a lighter object and produce a tight binary in globular clusters or other dense stellar environments. We will be able to distinguish between these kinds of formation mechanisms once we observe a population of these events. And I will not talk more about that, even though I could, because I'm out of time. I'll mention this. One more thing, a couple more things. One is that if we observe these loud events, they're nearby. There's a large population of them much farther away. They're not detectable as individual events because they're below threshold. But maybe they're detectable as a sort of stochastic random background of gravitational waves from all the very distant binary neutron stars and black holes in the universe. The more massive those binaries are, the lower frequency they will cut off. And if they are very light, like binary neutron stars, they'll look pretty much just like a power law. Okay? We will observe them directly in a redshift of less than like 0.1, 0.2, and then indirectly through the stochastic background. It's hard, but doable, potentially doable, and that's work being pursued by Tom. The future. We just finished our first observing run. We're going to be down for 6 months while we improve our detectors by as much as a factor of 2, and start a 6-month run in about July or August, which we'll call Observation Run 2. And then somewhere around 2018, we'll start a full year-long run, hopefully at design sensitivity or maybe close to it, around 2018. That we'll call that Observation Run 3. We hope Virgo will join us for Observation Run 2 in 2016, or 2017, so we're looking forward to that. This is very preliminary. At further, beyond Advanced LIGO, beyond 2020 or so, we will have third-generation detectors. And these detectors will be very aggressive, using squeezed light and squeezed vacuum and all kinds of fancy new techniques that you'll hear about if you go to Ryan's talk next week. And beyond that, space-based telescopes and potentially a telescope, a ground-based detector in Europe called the Einstein telescope, improving the sensitivity by factors of 2, 5, or more. much more. One thing that I can tell you is that when you're looking for something new, you never believe it's going to happen. And then when it happens, you just can't believe the reaction from people. And the reaction to this discovery was unbelievable to me. So much interest from all around the world, even from this guy. And I can tell you that this guy got 1 million page views in the first week. That just shut, and it's a beautiful. By the way, if you didn't understand anything in my talk, just go to phccomics.com and you'll understand gravitational waves. Okay, it's beautiful. Okay. Well, how do I end a talk like this? Let's see. Bumper stickers. We got to have bumper stickers. Okay. I have a bumper sticker, gravitational wave detection. But you know, that's good, but it really doesn't tell the story. You know, to really tell the story, you have to point out how damn hard it is, which is why it took us so very long. And it's not the end. It's just the beginning. We need to really detect a lot of these things so that we can do something much more accurate, like precision gravitational wave science. It's going to be even harder. Okay, well, I am out of time. But the advanced gravitational wave detector has begun. Detection era has begun. It will allow us to finally explore the gravitational wave sky, make unique tests of general relativity in the strong field, highly nonlinear and dynamical regime that physicists just love, make joint observations and discoveries with electromagnetic and neutrino telescopes, and open up a rich new branch of physics. But really what we look forward to most of all is the unexpected. Thank you. So long, everybody wants to leave, but I'll stick around for questions.
Right, so I know there's a lot of other events tonight. As advertised, the talk should go long. But let's...
free food. There's free food.
Right, so we're competing with fried chicken at this point. But why don't we, after those who need to leave very quickly, why don't we take about 5 minutes and see if there's 2 or 3 questions?
So, Alan, you mentioned observations from telescopes. Did you see this paper on the archive about gamma ray bursts? The Fermi thing.
Well, to be honest with you, I did.
Yeah.
Okay, what you're seeing here is the relative time compared to our event in seconds. The blue are the data points used to estimate the background, and the gray they don't use. And then they seem to see this excess about 0.4 seconds after our event. What do you think? They estimated the false alarm probability to be 0.2%. I don't know what that means. I don't know what to make this. What I can tell you, though, is that if it is associated with our event, binary black holes make gamma ray bursts. That's cool. This is gamma ray detector, by the way. It's Fermi GDF, gamma ray burst quantity. It also means that the light and the gravitational waves from an object 1.3 billion light years away came at the same time. Which means the speed of the gravitational wave, well, you've got to do the calculation. I can't do it. Really close to the speed of light. Darn good test. I sort of want this to be true, but I don't know what to do.
So you spent a lot of time explaining how you checked that the detector was operating well.
No, I spent very little on
But you checked very hard. So I know that LIGO has capabilities to eject signals. How can you be sure that it was not an accidental injection like some sort of malfunction?
You want me to tell that story again? Okay. Of course, the very first thing we thought when we saw this event is it's a blind injection. We had blind injections back in 2010. We wrote a whole paper about it. Just before sending it off to publication, we opened up the envelope. It was one. It really was a good exercise. It was a lot of work, but a good exercise. The very first thing we thought was this is blind injection. Okay? So we called up Gabby Gonzalez, the spokesperson for LIGO Center for Operation. We said, is this a blind injection? She said, get it out of blind injection. My best Argentinian accent. There it is. Okay. Anyway, so I said, okay. So we called the blind injection team. And the blind injection team said, there's no blind injection. So I said, can I look at the blind injection secret channel? And we have thousands of channels. Gravitational channel, we have the secret blind injection channel, which we are under honor to not look at. They said, sure, go to that. Okay, I looked, nothing there. Okay. Not a blind injection. Could have been a double blind injection, which means even the blind injection team didn't know about it. So I checked every single channel that we have, including the ultra-secret double blind injection channel. There is no double secret blind injection. It's not a double blind. As I mentioned last week to some of you, our immediate thought was that it's a triple blind, which would be a rogue, right? A bad guy, some disaffected employee who really wants to stick it to us, and shooting up the place isn't good enough. Injecting a signal and not telling you it, that would really screw us. All right. So we thought about this long and hard. You'd have to inject the signal and completely cover your tracks. So us, the experts, wouldn't be able to. So we thought long and hard and thought of all possible ways that we could cover our tracks so that we couldn't find it, and we came up with none. So we concluded that such a rogue person would have to be smarter than us. Okay, so there is no there is no triple blind injection. So that really only leaves one possibility: the evil genius hypothesis. Now, in the evil genius hypothesis, by definition, they're smarter than we are. Okay? We cannot rule out the evil genius hypothesis. I just like to think that a pair of binary black holes a billion light years away merging together is much more. Okay, that's my story.
Why don't we see if we have just one last question?
Right.
What you call mystery nodes. Have you looked at that as being a possible signal, as a physical signal? For
Yes.
example,
One of the first things that we thought of was that. Sorry.
For example, binary black holes or spinning neutron stars.
Right. Okay. So spinning neutron stars produce sine waves. These are not sine waves. They would be spectral light. Okay. Other kinds of astrophysical sources, you would see the same noise in both detectors. We don't. It's very different. It doesn't look the same at all. There's no coherence between the detectors in this mystery node. At some point, we thought maybe this is holographic noise from quantized space-time vibrations on the surface of our string brain or something like that. Holographic noise. Okay, so holographic noise you wouldn't be able to detect. It's basically space-time noise produced by the quantized gravity in the minds of crazy theorists. And those crazy theorists will tell you that the two detectors have to be almost on top of each other to detect this. So that crazy theorist, whose name is Craig Hogan and happens to be the head of the theory group at Fermi Lab. So this crazy theorist said, this is great, let's do it. So they built 40-meter long LIGO-like interferometers and put them right on top of each other at Fermi Lab. Look at these things. Between, over 5 years, they had to figure out how, or we had to teach them how. And they operated those detectors to look for Hogan noise, holographic noise. Now, the paper just came out a few months ago. No. Too bad. We thought it could be that, but it isn't. They will do it. Okay.
Let's thank our speaker one more time.